Hola. Bien. Well, can you hear me well? Yeah? Okay. So this talk is going to, we will talk about AI, deep learning, and all of these things that are in the media now. So I think it's very exciting. And yeah, this is my personal work about my investigation and how we could adapt all of these new technologies into the Scala world and Spark infrastructures. So maybe we will see some things that the good parts, the bad parts, a lot of things. So I will try to be a little bit fast. I don't know if you are in the world of deep learning, if you know all the concepts behind all of these language models. I'll try to do my best in order to be well understood by you. So if you have any questions, we can clarify after the talk, okay? So, yeah. As I have been working with Scala for a long, more than 10 years, doing data stuff, doing machine learning, microservice infrastructures using Akka, a lot of things. Okay. So this is the title of this presentation, A New Deep Learning Era. Well, if you see this graph, maybe you can see a lot of publications related to how these language models have evolved along of the last 3-4 years, and we'll see these new models like, we'll see models them are related to text, others to image, computer vision, and others are multimodal models. And well, we see here that we started with BERT. It was more or less 110 million parameters, and we can see how all of these latest years, all of these models, how the evolution or how they grew. So you can see models like GPT-4, other open source models that has been researched recently, like Llama 2, with billion of parameters. So you can see in a few years, all of these models, how the incredible evolution, all of these things, okay? So what we are going to see here is, we can take these models, we can adapt these models, we can adapt to do what we want to do, okay? And yes, the generative AI, I don't have to tell you about the Gen AI is, something that is every day. Everything that is these powerful techniques are going to be able to do in our day-by-day job. They are going to change everything. Either governments are creating new laws in order to control. Wonderful. So even the people who have developed, the pioneers of this technology, are saying that be aware of that, how dangerous can be these technologies if we don't use them properly. So we can see here a manifest that were signed with very important people in the technology. They were claiming to stop during 6 months the research in this technology. So yeah, this is a big deal. This is a big deal that is going to change everything. But yeah, let's take a breath. Yeah, I know this is going to change everything. This is very powerful. This is very wonderful what is going to bring us in the future. But if you see here what is currently our reality is, this is not so easy to take these models and throw into our systems. You can see here that we have a very big data infrastructure that ingests a lot of data from different channels. And we have teams in a multi-tenant fashion. We have a Spark, we have Akka, we have Flink, we have Kafka that do the connections and connect all of these services. We take this information, we group this information, create view for business intelligence. We train models with Spark ML, we create pipelines. There are a lot of stuff developed to control of these things, security, networking. If you want to take this copy of this data to put in another external service, this is not so easy. So there are a lot of things here that prevent us to do something with all of these new deep learning models. So it is not so easy. So there are specific concepts that I would like to explain to you. I don't know if you are familiar with them, but it's the language model, which is the core concept of all of this technology. So a language model is a probabilistic model that tells if a word is what word is the correct word in a sentence given a previous context. It's just a probabilistic model. we see that models like GPT-4 are huge probabilistic models, huge language models. So this is the core concept of this technology. It's something that we have to know. It's something that we have to take into account with when we try to adapt all of these models. This is a language model. It's not magic, okay? So there are another very important concept, which is the word embedding, which is a representation of this concept of we have a dictionary, we have a natural text that consists of words, and we have some mathematical model that map this representation into a vector space, okay? That vector space codifies some kind of semantics, and there are some techniques that we can use to build this language, these embedding models, and we need them in order to do our NLP projects. So first, when we had any kind of language model, we took our dictionary, we put all of this, our words in an input text and try to map into a vector space. We concatenate this vector representation in our sentence. We throw to a deep learning to a neural network. We give some kind of labels to see, depending on our, in this case, sentiment analysis, text classification, and everything related to some kind of this. And we choose one last function, most of the times cross-entropy function, that tries to measure the distribution of the real data, the predicted data. There's some measure that tries to minimize this difference or this divergence between distributions, and you put all of this in your neural network and there's an optimizer that tries to minimize that error, changing updating the parameters of the neural network, okay? This is more or less how it worked before the language models. Obviously, you could use not a neural network, you could use support vector machines, other models, support vector machines, XGBoost, random forest, and so on, okay? Well, there was a problem here that models didn't work very well, so recurrent neural networks came into the scene, and they put the time dimension in all of these models, okay? Not only the embeddings, they incorporate which is what word is before another, and so on. So this is closer to the representation of the current neural network models. And here we have some example of an encoder or the decoder. You can see this kind of architectures and text summarization, text translation, and it uses recurrent neural networks, okay? The problem here was that these neural networks use some specific state from the encoder, and given this state, try to decode a new sentence, okay? So, given that state and some input for the previous word, the model tried to decode a new sentence. Well, the problem here is, we don't have... the problem here was when this sentence, the decoded sentence, getting longer, and the model more or less started to fail, okay? It was difficult to create a long sentence in the decoding state, in the decoding phase, okay? So, here is where the attention concept became. And here is more or less the same example, but not only the encoded state and the previous word give some influence to the new decoded sentence. There is some vector context, the attention context here in the yellow circles, more or less, that when a new word from the decoded state appear, it takes some input from the input sentence, for the origin sentence, okay? So a new word has some influence for the input text. That improved a lot this kind of technology, the attention model. And here is where we have our start here with the transformer model. The transformer model is the building block of every single model that you see now in generative AI. So it takes the attention concept to the extreme, okay? It puts a lot of transformer layers, one on top of another, on top of another. Models like BERT or Roberta, they use 12, or now models like Llama use 40. So it is the main building block now in these models. You can see here this from the first publication, this model. And models now don't follow this design. They change more or less. They are only encoders models, only decoders models. So there is a mix. They don't follow this specific architecture of the transformer model, but it takes more or less the concept. Okay. So this is a sample of a very well-known. Maybe you can understand. You can know about all of these BERT models. They are encoder models that are built on top of a transformer architecture. There is a very important concept here that I forget to say. This is transfer learning. So these models are generative AI models, encoder models that are pre-built in a pre-training phase. Okay, we take this pre-trained model and we adapt this model into our business case. That is what BERT and other models like BERT work. Okay, so they take one pre-trained phase, which is in BERT is to the pre-trained task, which is the masked language model at the next sentence prediction. That task that creates the language model. So they put a lot of input corpus, and they try to, for example, in the best market language models, this task put some mask in the input sentence, and the model tries to find which is the missing word. Okay, so doing this about days and days and a lot of GPUs hours, they're trying to understand or try to create a language model, which is what I saw before. Okay, and then we take one, for example, here we can see that there is this box, the dense, with a dense layer representation of a neural network, and a softmax, which is function, activation function that creates a valid probability function in the output. So you can put this block on top of BERT, and you can do downstream tasks like sentiment analysis, test classification, entity extraction, and so on. That is why this model works. Okay, how this model works. So here's the generative AI. You can see here's the GPT-2. It started 3 years ago, more or less, and we see different sizes of this model. And this model is a little bit different from the encoders like BERT. They are trained in a different way, but it uses the same main core based in transformer. Okay, so what we are going to see here is some implementation using Scala 3 and Apache Spark to do that kind of things. I'm not saying here that we have to throw away the wonderful frameworks that we already use and day by day, like the PyTorch or transformer library or GPUs. No, but in this time, this is very. I think it's very important to know what we are in our hands, and we need to know how to adapt ourselves to different situations. And what I will I show here is how the good and the bad parts of the Scala environment and the Spark environment have in terms of how to create that kind of models. Okay, so we have our hypothesis, and we say, okay, can we adapt these models that have been trained in these big data centers and put in our infrastructure that is based in Scala and Apache Spark? We already have a multi-threading, multi-node infrastructure. We would like to use Spark, which is running in a Kubernetes schedule using or Jan or in the Spark alone. I will say Mesos, but Mesos is already deprecated. So, and using Scala 3, we know that Spark, you can use Scala 3 and since Spark 3.2. And using only SIMD CPU instructions like AVX2, AVX 512, not GPUs at the moment, okay? It sounds a little bit disruptive, okay? We will see if we can do that. So what are our use case? First of all, we have the text classification is the I think the most easy case that we can handle. So we have textful text that come from the, say, data center, newspapers, or whatever. And we try to give some label, to put some label to it, different text, input text, okay? We have name entity recognition. That is something very important. It tries to put labels on some tokens and documents. Here I put text generation, which is generative AI. We are not going to see this. You can do that even with encoder architecture, but most of the time you will use something like GPT-3 or Llama. And Q&A, text summarization, medical, there are a lot of use cases that you can build with all of this technology. So in this case, we are going to see one simple text classification using Roberta. Roberta is another specification on transformer encoder. Base encoder is an evolution of BERT, is trained in a different way. It only has the Muscle language model pre-trained task. So this is not the next sentence prediction like BERT. So it's more or less in that point easier than BERT, but it's more complicated because it uses a different tokenizer. So it's bigger, the tokenizer, because the input dictionary or input tokens are more than 50,000. And that we are going to do here is build all these models using Scala. We are going to put this dense network with an input of 768 dimension vector, which is the hidden dimension of the model, and the end that corresponds to the number of classes in our case, okay? If we have 4 classes, we put 4. If we have sentiment analysis with 2 labels, we would put 2, for example, okay? So where do I find a pre-trained model? Now, I think if you are working with all of these technologies, you can see that there is a very important hub now, which is the high interface hub, where a lot of companies, a lot of public institutions put their pre-trained models, okay? So we are going to do here is look, try to figure out what would be a best pre-trained model, try to download, try to convert this model, and try to put it into a Spark, okay? In order to do a fine-tuned task. I use here this Roberta base trained with data from the National Library of Spain, it was done by the Barcelona Supercomputing Center, which is a public institution that does that kind of things and other things more. Okay, but they released this pre-trained model in 2021, 2 years ago, more or less. They released the Roberta base and the Roberta large, which is 400 million parameters, and another version of GPT. Okay. So we have here the model is built using PyTorch and powered by GPU infrastructure. So they have been trained. It's small. It has been trained for more than maybe 3-4 days running, and a lot of GPUs. More than thousands of the specifications of the training phases in the high-end phase page. And how we can take all of this model and how we can put all of this model in our distributed platform. So use the standards. So we have PyTorch model. You can convert that PyTorch model using ONNX runtime, which was created by Microsoft. And we have a generic representation, so even frameworks like TensorFlow or Ajax are compatible, can export this model, its internal models in this framework. So I take this ONNX definition and I try to put my graph in my Spark infrastructure within that ONNX definition. So this is more or less the picture that can represent what we are trying to do here. We have the input model. Yes, we have PyTorch, which is built in Python. We use C++ or CUDA, and we have a GPU, okay? A GPU or more GPUs, okay, running in parallel. So we should transform that model representation into our ONNX representation, which is a generic representation. ONNX support multiple backends. Not only GPU, it can run on CPUs, backends with different technologies. And we try to read that generic representation and put into our distributed platform, okay? we have Spark and we have Scala. I put here C++ because linear algebra libraries by vendors are normally codified in C++. They are native libraries, okay? Like libraries MKL, or other libraries that can take benefit all of the capabilities of the CPUs doing vectorized operations, okay? So this is more or less the picture that we are going to do, that we're trying to do in this presentation, okay? So we have here some question. So what is the deep learning framework that we're going to use in Apache Spark, using Apache Spark? So there are a few, but I have been working with this, was developed by Intel guys. And it is built on top of Apache Spark. There is no extra protocol. So it uses Spark primitives to do the distributed training. Now has changed because BigDL project is a set of projects, and the project that use the deep learning library is called DLLith, and that provides some Keras-like approach to build models in a functional way. So we can build our transformer block, our set of transformer blocks using that API, and it distributes the training phase. So if we have 50 nodes, for example, with 8 cores per node, it tries to distribute the training phase in all the available resources. Okay, it does model distribution, so it puts the model in every single node. It starts to train in parallel, and there is another synchronous task, which is the weight synchronization. So every single node has to have the same weights in each iteration. Okay, more or less is how it works. So we are going to do that. We are going to use BigDL DLLith, and we are going to build the graph. We are going to import the model from Hugging Face. We are going to convert to NNX, and we are going to execute a fine-tuning task into our Spark cluster. Okay, and most important of this is we are going to use Scala 3.3 and a version of Spark, Scala 2.13. One thing here is that I have been searching in all the different Spark providers, like Amazon, Analytic Insights, Dataproc, and none of them deploys a Spark for Scala 2.13 in this time. I have read that Databricks maybe soon is going to deploy one Spark version that supports Scala 2.13, but at the moment it was only testing in a specific environment I create personally. There's no way now to test in that kind of products. Okay. So this is a graph. We are going to have here our Roberta encoder, and we are going to build a dense neural networks and lots of mass to create the valid output probability distribution. Okay. So here's the code. We create our Roberta base class. This class have a lot of input parameters. So we have a length of 512 tokens, input tokens. We have here a hidden side, which is the internal vector space representation. In this case, Roberta is 768 vector dimension. And block is the number of transformers blocks that we are going to put sequentially. And there are another parameters like use low rank adaptation, which is a technique that already can be used. And this head layer that is going to be our dense representation in order to do the downstream task. Okay. You can see here that this extends from a Keras layer, the model, because BigDL, the DLF is based in some way Keras representation. Okay, it's a functional. You can build models using a functional approach, more or less like Keras does. Okay, And here we have a tensor numeric representation, which is the instance that's going to apply the linear algebra operations. You can see that it has a type parameter. This model, this framework now supports float and double, so is floating point 32 for float and bigger representation, even bigger representation. So this is what this framework supports now. So this class represents the graph, and it includes 12 transformers layers with 12 attention heads. This is something that comes from the transformer architecture. Okay, it has two embeddings for the token and another embedding for the positional embedding. If you remember, as we saw with the recurrent neural networks, there was one time dimension. That time dimension is what this positional embedding does. Okay, so this is the how we build the model. We have here the word embedding layer, a positional embedding layer. We make element-wise addition to create another embedding. We as you can see here, we use this functional approach. We have the embeddings node. We having this layer normalization node make one sequential decomposition using the two nodes. Okay, we create another node. Layer normalization is some technique in order to do more stable the training phase. And the dropout, which is another technique that is using deep learning in order to prevent the overfitting of the neural network. Okay. So this is the first step, is creating the embedding. Now we have here how the attention works, how we can create attention model, and which is already explained here. We have here the three matrices in the transformer model that creates that attention. This is the Q, the K, and V. Okay, so we use the dense representations that are models that BigDL provides, and we take this representation, we stack this, we create these matrices, we perform the attention here in that function. Okay, so first we split in a multiple heads the procedure. We create attention in different heads because you can parallelize that attention. It depends on the hardware, it depends on other things, but the attention heads, which is something that is created inside a transformer model, more or less how it works. So we have the three matrices here, we create attention, and so on. We merge all the results, we create another dense representation. This is more or less what a deep learning project when creating a graph works. Okay, so if you're not familiar, maybe it can serve as an introduction, but it's more or less the same in a lot of projects and a lot of architectures, neural network architectures. So, and then as a result, the final is to put a dense representation for our downstream task. Here we have the dense layer and with an activation function with the logs of mass activation function. Okay, that gives the valid probability output distribution, which is the distribution that codify high probable is one label for an input test. Okay, here I put some example envision transformer that is more or less the same, and it's not natural text, but images in vision transformer were more or less the same. Okay, and we have here our Spark environment is ready to start. Then we have the data frames. We created data frames, the train and the validation data frames, all related with the Spark. It's SQL. Okay, we use once we have the data frames, we have to tokenize the data frame. Remember, we have to put that words in a vector space, but we have to extract the tokens. So tokens are identifiers, integers that say, okay, this word is this integer, or the word is this integer, or this fragment of this word is this integer. That integers are mapping into the embedding. Okay, so we have to do previously, before the training phase, try to adapt to create the tensors or the matrices that are going to feed the neural network. So we have here the train tokenized, the validation tokenized. We build our Roberta first sequence classification with a length of 512, with a hidden size of 768, and we create we say here the samples. The samples are the tensors, the input matrices that are going to feed our neural network. But first, as we said before, we have to convert the PyTorch model to ONNX. We save the representation into BigDL, and then we feed the model. Okay, we are going to choose a batch size of 32, 5 epochs, and we are going to say, well, this is the category column, and so on. So things that are necessary for the train to start, okay? So yesterday I just made public the code that, all of this code and all of the experiment that you can run in your Spark 2.13 cluster, remember? There's no more Scala 2.12, there's no more Spark. This is something that is, well, in my opinion, it's a little bit difficult because everyone is working in Scala 2.12 now. Even frameworks like Spark and NLP, they haven't released the Scala 2.13 or XGBoost. All of them are still working in Scala 2.12. So in BigDL, we released one branch. So the Intel guys, I was working with them in order to put one branch, experimental branch, but you have to build from sources from my forked branch from BigDL because it's very experimental of the changes that I've been doing in the framework in order to support Scala 3 and some improvements in terms of operations in some mathematical operations. Okay. So what are the downsides of all of this thing? As I told you before, well, we know that there are wonderful frameworks that use this technology that are the main actors of this technology. One is PyTorch, one is the transformer library for Hugging Face. Even TensorFlow has lost a little bit of attraction. And yeah, should we throw away all of this technology? No, this is a very good technology, very good products. But this is something that I tried to convert all of this world into the Scala world. So it's a lot of things to do yet, but the process can increase the batch size. So if we have a lot of threads in our Spark cluster, we can use hundreds of threads to do the task. Okay, there's no problem at all. So this is the real power of this approach. So you can take leverage, or you can take advantage of your cluster, your existing cluster. And because this is a Spark application, a normal Spark application, all the policies that you have applied previously to other Spark applications, they still work here. You don't have to enable anything, okay? But there is a lot of drawbacks in this. The approach is like this put a lot of pressure on the GVM because the representation of these tensors, internal tensors, are then flow at 32 now. So it increases a lot the heap of the GVM. Some BigDL, DLLib, tensors are, in essence, are Scala arrays with some additional information. So memory is handled by the GVM. It is not bad because I see the garbage collector time of the garbage collector is not a bug. I think it's something that you can manage more or less. But the problem is the lot of memory that it consumes. So if you want to create a big batch size of 128, you are going to need very good big machines. I'm talking about 300 gigabytes for 3 machines of this kind of size. So this is not something that you can do properly in a small Spark installation, okay? That is something that we have to improve. So there are a lot of techniques now that tries to reduce that representation. I don't know if you follow the open source of generative AI these days. You can run a Llama model in your laptop because it uses 4 bits quantification. So it reduced a lot the size of these models, okay? And we are not at that point today, but we will do in the future if the community likes the kind of approach in Spark. So, well, in every iteration, weights are synchronized. It depends on the network. The model, this framework does 8 bytes quantification in terms of reduce the size of the model when it's transferring across the nodes. And yeah, there is not much in overhead. It doesn't use a carrier approach. So in each iteration, it is there are 2 Spark jobs, one to calculate the gradients in each thread, and another job to do the weight synchronization. Okay, so more or less there are more drawbacks, but yeah, I think the most important things are the memory that you need to do something that is comparable to the GPU's approach. But as I said before, there are a lot of things you're following how the open source community are working now. It's very impressive, all the things that they are doing. Like the Llama CPP project is something very, very wonderful in my opinion, very, very, very nice. So you can convert all of these representations in a int4 representation, which is, you can take one Llama CPP 3 billion model and you can run in your laptop. And it works more or less well. It depends on the size of the input sentence or the input prompt, but it works. And it's a very good things that already have been done there, okay? So there are a lot of things that we can take from that open source frameworks and put that kind of approaches in our Spark implementation, okay? Yeah, I was talking about quantification, understanding int4 quantification. It reduced 8 times because if I have a 32 floating point representation, if I convert that model into 4 bits, so imagine there are a lot less pressure in my nodes. But, well, there's trade-offs, maybe precision and accuracy in terms of the models maybe can decrease. Yeah, there's a lot of research about that, but results are okay. More or less, you can handle that loss of precision. There is another approach, which is the low-rank adaptation or large language model. This is very interesting because remember, when we are trying to update all of these parameters of the neural network, if we have 125 million parameters every iteration, we have to update all of them. This approach says that, well, instead of changing or updating all of these parameters, why don't you change a few points of this model and you leave the model without touch anything? So this is very, very good because you reduce a lot the memory. So when you do the forward phase, you have to store the intermediate outputs of the layers in terms of calculated gradients. And if you, for example, here we can see that the Roberta, instead of tuning the 125 million parameters, you only have to train the 1% of the parameters in each iteration, which is something which is amazing. So it's something that leaves us to do a lot of projects of using this technology, much more projects, many more projects using this technology because we can parallelize more, okay? Yeah, I don't know how much time I'm going to finish now, okay? And yeah, there are a lot of things to do in this world. There are a lot of services that are being built. There's going to appear a lot of services building in open source, using Llama, using Falcon, all of these models use this infrastructure, this attention infrastructure using Transformer. Has the drawbacks. We have to convert. We have to know how all of these models work under the hood. If we need to adapt ourselves to other infrastructures, if we want to apply some policies, if we want to transform that knowledge into our necessities, our needs, So a lot of things to do. I hope you find interesting my implementation in the Spark infrastructure about all these things. There is, a lot of improvement, but it works. So you can test. There are all the instructions in the GitHub repository. Maybe you can find interesting. Okay, thank you.